Welcome back, everyone, to podcast 2 of week 10. We're now continuing on into strong and weak acids, which, to be honest with you, is a review again of Chem 20. But relating this to an acid ionization constant, that's definitely new. Now, it's an acid ionization constant. And even though that sounds all fancy, really it is an equilibrium constant associated with the equilibrium law of an acid. Okay, so first of all, let's, like I said, review a little bit. Strong versus weak acids. Ultimately, even if two acids have very similar concentrations, like let's say, for example, they both have a concentration of 1.0 mole per liter. Regardless of if concentrations are the same, their characteristics often differ. And this is something that has to be explained. So when you see empirical evidence, we're like, wow, why are we seeing this differentiation from one acid to another? Then we have to explain the evidence. Now, characteristically, those stronger acids tend to do a few things. For instance, they react way more vigorously with certain metals. For example, magnesium and zinc are good metals to indicate whether something is a strong or weak acid. Honestly, it's just a good test for an acid in general. The next thing is, even though both strong and weak acids will have pHs less than 7, the strong one will have an even lower pH. So you'll see a pH of 1 or 2 versus a pH of 3 or 4, for example. Next, the electrical conductivity will be significantly better in a strong acid than a weak acid. And what affects conductivity? Well, ultimately, it's the amount of ions present. So all of this is somehow relating to the strength, the amount of ions, okay, etc. Let's talk about this. So ultimately, the stronger the acid means the greater the ionization that occurs. Ultimately, if you have a strong acid, they ionize completely in water, 100%. Totally, fully. Now, for example, guys, last year you had 6 acids that we told you memorize these strong acids, know what they are. You get a bit of a break in Chem 30. If you go in your data booklet and check out page 8 and 9, these are the ones that are sideways in your data booklet. I flipped them over here. And I want you to notice these right here. And hey, we got 1, 2, 3, 4, 5, 6. Dun, 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 dun. Guys, here are your 6 strong acids. These are the exact same ones that you were asked to memorize last year. And ultimately, all 6 of these will undergo 100% ionization every time. So your job is, whenever you hit a question now in an acid, you need to do one of 2 things. You need to memorize these again and just know by seeing it, or you need to refer to this sheet, this page 8, and be like, oh, is this one of the 6? Yes or no. This is essential. You need to do this for your questions, or potentially you're going to get a whole lot of questions, not kind of wrong, but seriously wrong. Okay? Alrighty. Now, let's continue talking about an example of a strong acid. We'll look at hydrochloric acid, definitely one of those 6. And ultimately, because it is strong, we end up with that one-way arrow. In other words, we say it is quantitative. A quantitative reaction means that all of the reactants quantitatively will be transformed into the products. Hence, look at the concentration of the hydrochloric acid. It is the same as the concentration of the hydronium after completely being reacted, and it is the same as the concentration of the chloride too after being completely reacted. Why? Well, guys, these are a 1-to-1 ratio, so this is pretty logical. Okay, remember, this original concentration is before it ionizes. These concentrations of the products are after that 100% ionization. Keep in the back of your head, strong acid. Okay. Okay, what about a weak acid? Now, weak acids characteristically only partly ionize, and this should look familiar. Equilibrium arrows, guys. That's why these acid-base systems work so beautifully into our equilibrium unit. Now, first, recognize that the concentration of this acetic acid is the same as that concentration of the strong hydrochloric acid we looked at. Acetic acid is not one of the six. Anything that's not the 6 is automatically weak, okay? So if it's not one of those strong 6, bam, it's weak. Now, prior to ionization, we have that 1.00 molarity. After it reacts with water, and same dealio, guys, in terms of this reaction with water. There's a proton transfer, the H plus moves over, hence we end up with hydronium, right? But notice these new concentrations, 4.24 times 10 to the negative 3 moles per liter. And then, of course, identical for the acetate ion. That is significantly less than a 1-to-1 ratio. So very much so, this is not 100% ionization. It is a partial ionization. This is an equilibrium system. Now, just from a diagram perspective, ultimately when you have a strong acid, like what's on the left here, this diagram is showing you a 100% quantitative ionization. That's why there's none of the original acid, which we call HA. You'll get used to that lingo, right? And everything is changed into the H plus, meaning hydronium, and the conjugate base, we'll say. Vice versa, take a weak acid, and we have a scenario over here where there's actually a massive amount of the acid that stays unionized. It doesn't ionize, only a little bit turned into hydronium and a little bit turned into that, what we call conjugate base, the anion. Okay? Weak acid versus strong acid. Alrighty, when you compare, just as a side note, the pH of these, this gets interesting. This is still relating back to the same example I was just giving to you. So the hydrochloric acid completely ionizes, so the concentration of hydronium is the same as the original HCl. And look at that pH when you calculate it. Negative log of the 1.00 molarity. Oh yeah, low pH, 0. Vice versa, the acetic acid, which partially ionizes to this concentration of hydronium, when you calculate this, there is no question it is an acidic pH. 2.373 is fairly acidic still, but it is acidic, it is below 7, but it is not as acidic as the hydrochloric acid. Okay. Now, putting this a little bit further into context, guys, let's look at it more as an equilibrium system. Because ultimately, if you look back, to here, that's the key, right? We've got those two-way arrows. So these weak acids, not the strong, these weak acids are equilibrium situations. And if that equilibrium exists, then we can create an equilibrium law for weak acids. And if we can create an equilibrium law, we have an equilibrium constant. That equilibrium constant is called the acid ionization constant, otherwise known as Ka. It's based completely on the concept that every acid will ionize in water to different extents, to be sure. And really, this acid ionization constant just tells us how much they ionize. The bigger that Ka is, the bigger the equilibrium constant is, the stronger the acid is. In other words, it seriously favors the products. It favors the hydronium more, thus making a stronger acid, right? Those are those very large Ka values. Now, remember once again that language I used. A strong acid is quantitative, completely ionized, in other words. Looking over in your data booklet, if you check out this page 8 and 9 has Ka values listed on it. Whoopsies. There we go. Right? So there's Ka. And notice for those 6 acids, we don't even write the actual acid ionization constant. We just say it's very large. There's a lot, right? It's super high. These things are quantitative. Yep, super big. All right. Imagine then this would be a generic reaction for a strong acid. a generic ionization, if you will. Now, we write H, of course, to be the hydrogen that has to be there. A would be whatever the hydrogen is with. For example, hydrochloric acid, H is the H, Cl would be the A. In every situation, it's reacting with water, and in every situation, one proton will transfer, one proton, right? That's how we get hydronium as a result. And if hydrogen leaves the A, you're left with the ion. In other words, with hydrochloric acid, this would be the Cl negative anion. It's pretty logical when you put it in context with a actual acid that you could analyze. And I mean, if you imagine an equilibrium system for these guys, then you're going to see that ICE, so we'll make an ICE table, okay, that initially you have some initial concentration of your acid, right? And then it's going to go down by an X value, but because this thing is quantitative, you know this is going to go down to 0. Water's a pure liquid, doesn't relate to the equilibrium, okay? Go to hydronium. At the beginning, initially, we don't start with any hydronium, 0 mole per liter. We don't start with any of the anion, 0 mole per liter. These are 1-to-1, so they go up by 1x. That means this is essentially going to go up to whatever the initial concentration of the acid was. And same thing for the anion. It's going to go up to whatever that initial concentration of the acid was. There we go. In other words, for any strong acid, you're going to have a situation where the concentration of that original acid is going to be exactly the same as the concentration of the hydronium. This, though, this only holds true for a strong acid. If it is a weak acid, not happening, okay? So let's say you're given a question. The very, very first thing your brain should do is be like, hey, check out the acid that has been given to me. And when I check out this acid, is this thing weak or is this thing strong? That has to be your starting point, because the way you analyze it is totally different for a strong acid versus a weak acid. HClO4, which is perchloric acid, not a new one, guys, something that would have come up to you last year. And here it is, perchloric acid. It's a super strong acid, which means it is a quantitative ionization. So similar step-by-step process to what we would always do with these is we would show the ionization equation. So we have HClO4 aqueous plus water, H2O liquid. You're going to have the proton transfer. And because this thing is strong, it is quantitative, so strong acid. We're going to end up with our ClO4 negative, which is the anion, the A, plus hydronium, H3O plus aqueous. There you have it, quantitative ionization. Now, we've been given the original concentration of the perchloric acid, the HClO4, and that's equal to 0.36 moles per liter. This is quantitative, right? That's the key, the one-way arrow, which means I can take the ratios exactly as they are. Divide by 1 mole for the perchloric acid, times by 1 mole for the hydronium, 1-to-1. I just found out the hydronium concentration in this particular circumstance. It's identical, 0.36 moles per liter. And guys, that's one of the questions that was asked. What is the hydronium concentration? Once you have that, once you know for sure hydronium, pH is easy. pH is equal to negative log of the hydronium concentration. Oh, see, no big deal. Negative log 0.36. There was no rounding we had to do here, right? We didn't do any. But regardless, always use the long original values, right? Only round at the end of what you're trying to figure out. So we found hydronium, that one is done. When we use hydronium again, use the unrounded value. My pH though now should be rounded because I'm just going to finish there. 0.44 pH Indeed, a very low pH, indicating this is absolutely a strong, strong acid. Okay, so when you hit a question and you recognize, yeah, we have a strong acid, your brain should really be going, boo boo, this is easy, because they are easier questions. They're fairly simplistic. They're ones you could have done, in all honesty, in Chem 20. When we move into a weak acid, and this is a different twist. Now, weak acids, of course, have much, much smaller Ka values. And the equilibrium constant, Ka, is smaller because the products are not being favored at all. It's the reactants, right? Much, much lower. It is a partial ionization within that equilibrium process. Look back at your data booklet and start examining these guys. Look at them as we go. These are all weak acids, and check out those Kas. Quite low, right? Like 1.4 times 10 to the negative 4. Move to the next page. We get all the way down here, 4.8 times 10 to the negative 13. These are small numbers. So the Kas of weak acids are indeed quite small. And ultimately, from a general equation perspective, it looks a whole lot like the ionization equation of a strong acid, except, and it's a big except, this one's at equilibrium. It is not quantitative. There is still a proton transfer. There is still hydronium that is forming, but we have that double arrow representing equilibrium. Hence, we have an equilibrium law, okay? And the equilibrium laws of weak acids are something you will become very familiar with writing. Now, guys, I saw a few of you when you were doing your assignments have issues with this. Equilibrium law does not have any numbers substituted into it. It has the original reactants and the original products. So make sure that you are indeed, for all of these questions, actually writing the equilibrium law before you start substituting concentrations in. Very important. Okay, check out this example. 0.25 molarity solution of hypobromous acid. Okay, cool. What's hypobromous acid? Has a pH of 4.65. Calculate its Ka. Now, hint, hint, calculate its Ka. That means you can't go over here and find it. It's not going to be one of the listed Kas. That's why you have to calculate it. Okay, so hypobromous acid, not one of the strong acids. How do I know? Because I glanced through that list of 6 and go, it's not one of them. Ding, ding, ding. There we go. Your first step with this always needs to still be writing out the balanced chemical equation. And in this case, it is a balanced acid ionization equation. So we write the acid, HBrO aqueous, being added to our liquid water, of course, and it is weak acid, so equilibrium arrows. We're going to take away this hydrogen, right? The proton transfers. So when hydrogen leaves, it's H+. That must mean that what is left is BrO negative. Why? Because positive 1H plus BrO negative would give us the original HBrO neutral, 0. Okay? We're also left with, when that proton transfers, hydronium, H3O plus aqueous. Now, guys, here is that scenario where very, very much so we're dealing with, like I said, an equilibrium system. We have an initial concentration of everything. We will have our change in concentration, and we will have our equilibrium concentrations. You're given the concentration of the hydrobromous acid. So that 0.25 molarity goes here. Now, water, again, it just gets scribbled out because pure liquids don't have concentrations. The bromate ion on the other side, or the bromite ion rather, is at 0 because initially there isn't going to be any. So this one starts at 0. Same thing, hydronium starts at 0. This is balanced. Everything's 1 to 1. So the hydrobromous acid is going to go down by some X value, and the bromite is going to go up by that same X value, and the hydronium is going to go up by that same X value. The question is, well, what is that going to be? What is the final concentration? And this is where knowledge of pH comes in beautifully handy, or pOH if the case may be. If I'm given pH, I actually have enough info to get the hydronium concentration at equilibrium, right? That is what pH is. It's the amount of concentration, or the basically relates to the concentration of hydronium. So let's do some number crunching here. We know, calculation-wise, hydronium concentration is equal to 10 to the negative pH. And in this case, pH is equal to 4.65. So I plug that in. Don't round, right? You got other stuff to do here. H3O plus is equal to 2.2387 ... times 10 to the negative 5. Doesn't really look like it. There we go, negative 5 moles per a liter. Other words, guys, you just found X, right? This is what the original concentration went down by. This is what hydronium concentration is. So we now have this value. I'm going to write it in a different color, in green here. We just found the hydronium concentration, 2.23872 ... times 10 to the negative 5 molarity. If that's what hydronium went up by, these things are 1 to 1. So the bromide went up by the same thing. In other words, it's also 2.23872 ... times 10 to the negative 5 molarity. Sorry, my pen's going out there. Now, what about the hydrobromous acid? You can see how this has changed as well. We've figured out the value for X, right? So ultimately, we need to take the original concentration, that 0.25, and subtract by the 2.2387, blah, blah, blah. Subtract by the X. When you do that number crunching, you end up with 0.249977 ... moles per liter. Okay, look at these values. I have the equilibrium concentration of hydrobromous acid. I have the equilibrium concentration of the bromide. I have the equilibrium concentration of the hydronium. Think about what this means. Okay, those are all at equilibrium. I also have the ability to create an equilibrium law. Ka equals concentration of the products, BRO negative aqueous, to the exponents of their coefficients. These are coefficients of 1, so that's super easy. H3O plus aqueous divided by the concentration of the HBRO aqueous. Guys, equilibrium laws are concentrations at equilibrium. In other words, you have all these. You know the bromide concentration equilibrium. You know the hydronium concentration equilibrium. You know the hydrobromous acid concentration equilibrium. Why? Because we just number crunched them. We just found them all out. So let's plug in the numbers we know. It's going to be that 2.2387 ... times 10 to the negative 5 moles per liter. And it's that times itself again. So I'm just going to put squared because I can be lazy that way, right? Why not? We know that the hydrobromous acid has that concentration of 0.249977 ... moles per liter. Number crunch, figure it out. Look back to the original question. Whew, here things are getting messy. pH, guys, 2 sig digs, not 3. The 4 is not significant. My original molarity, 2 sig digs. I need to have a Ka with 2 significant digits. In other words, we number crunch, we get Ka equal to 2.0 times 10 to the negative 9. Highly recommend, as you're going through these podcasts, you are pausing and trying to do the number crunching yourselves, making sure that you are getting to the same number answers that I am. All right. Whew, little twist, right? Hopefully that feels okay. Now, what if you have a question where the Ka value is one from our chart? So it's something that you can now use the Ka for in order to find out the hydronium concentration and in turn then find out the pH. Remember, guys, weak acids. That's what we're dealing with these equilibriums. Now, little side note here. This is going to come into play. For weak acids, guys, the equilibrium concentration of the acid is said to be equal to the initial concentration of the acid. Now, in actuality, are they identical? No, they really aren't, but it's so close that from a number crunching perspective, it doesn't actually make a difference. So you're going to see me doing this through the examples, and it's an important note for you to recognize as you work into the assignment. Is there a way to do this without making that assumption? Sure, it involves the quadratic formula, and it gets kind of fun. We don't require you in high school chemistry to go into mathematical analysis of that sort. Mathematically, is it more correct to play with the numbers from a quadratic perspective? Totally. If you go into university chem, yeah, absolutely. But for the sake of what we're doing, this holds true. And I'll put that into practice in the next question. So let's try it out. First things first, and I've said this before, you need to recognize in a question if you're dealing with a strong versus a weak acid. This is huge, because if this acid was strong, this question would be super easy. It would be no big deal. Because it is a weak acid, your brain has to go ding, ding, ding. I need to deal with equilibrium and equilibrium laws. So let's start by writing out the ionization equation. We have HCN, so we have this weak acid that is going to react with water to ionize. We have the hydrogen proton that's going to transfer from the HCN to the water. Equilibrium arrows, that's huge. We're left with the anion CN negative, and we're left with our hydronium. Okay, so this weak cyanic acid, right? Now, equilibrium arrows means absolutely we have an equilibrium situation. So we'll have an initial equilibrium, we will have a changing equilibrium, and we will have our final equilibrium. Our original concentration of the cyanic acid is 0.36 moles per liter. Okay, now keep going. What happens next? Well, it is going to go down by an X value. So this is similar to what we've done before. Water we leave out, it's pure. Same as before, the cyanic acid is going to start at 0 moles, the cyanate is going to start at 0 moles, right? There's nothing there before it ionizes. The hydronium is going to start at also 0 molarity, nothing. If the cyanic acid goes down by X, this is going to go up by X, as is the hydronium. What is 0 plus X? It's X. 0 plus X, X. Easy. How about for the HCN? Well, technically, it is 0.36 minus X. But what I'm trying to tell you is that is going to make such a small difference. It's really not going to change us numerically. So instead, we simply use 0.36. And that, folks, is extremely important for you to recognize. And that is the point that it is being made here. That we say the equilibrium acid concentration is going to be the same as the initial acid concentration. In other words, we are going to use that 0.36 again. That's key. Okay. Well, now what? Where do we go from here? We need to try to figure out what on earth X is. In other words, what is that hydronium concentration going to be? Now think about what this is. This is HCN. So if you go over to your data booklet, this is something that we can hunt for. And let me just clear it off so we have a clean page. You're going to have to get used to scanning this thing, right? Going all the way down here, all the way down here. Where can we find this proper one? Well, here it is. Okay, oops, that's the wrong thing. HCN, which relates to a Ka of 6.2 times 10 to the negative 10. Yay, we have something to plug in for Ka. So let's do that. But first, create your equilibrium law. In other words, Ka is equal to the concentration of the Cn negative times the concentration of the hydronium divided by the concentration of the HCN. There it is. Plug in what you know. For these, honestly plug in first before I rearrange. Your call how you wanted to do it, guys. 6.2, I got this from the data booklet, right? Times 10 to the negative 10 for Ka equals concentration at equilibrium of the cyanide, the CN, is X. Concentration of the hydronium at equilibrium is X. I can divide by 0.36. Ultimately, that means we have 6.2 times 10 to the negative 10 equals X squared over 0.36. Let's keep going. We need to get X by itself. Ultimately, X is going to be equal to, and I'm going to already take away the square there, the square root of that 0.36 times Ka, 6.2 times 10 to the negative 10. All I'm doing is algebraically rearranging that previous equation. Number crunch, guys, make sure that you're being careful with your calculators. That's not a calculator error that is getting you a wrong answer here. We get 1.49398. Have the whole number down. You're going to need it again. Times 10 to the negative 5. Now, what does this relate to? Well, guys, this is X. And X is hydronium concentration. We just found part of what the question asked for. We need to put this according to the question of here, 2 sig digs, okay? So 2 sig dig wise, my hydronium concentration is 1.5 times 10 to the negative 5 moles per liter. Part of my question has now been answered. Part 2 is the question says, what's the pH? Well, pH, if you've got hydronium concentration, is beautifully easy. No big deal. pH is equal to the negative log of the hydronium concentration. Easy peasy. So start plugging stuff in, but remember, use the unrounded value. Don't plug in 1.5 times 10 to the negative 5 here, guys. Go back and plug in 1.4939, and trust me, this can sometimes make a difference, so make sure that you're watching that. Times 10 to the negative 5, come on, 5 moles per liter. Plug it in, number crunch. Now we need 2 sig digs. pH equals, the 4 is not significant, 8.3. There it is. Lo and behold, we now have a hydronium concentration and our pH of a weak acid. Whew! And I'll remind you again, this Ka for the HCN came from the booklet, right? We got it right here. So you're going to have to start to look for these and utilize them. Alrighty, let's do one more question because I recognize this can be a little bit wonky and a little bit tough. So here's another example of a very, very similar type thing. So we've got a weak acid, right? HOCl. How do I know that? Well, because I can go over here to my handy dandy formula sheet and I can start to look through things and see, oh, there it is, hypochlorous acid. And there is my Ka, 4.0 times 10 to the negative 8. It is not one of these 6 acids, therefore it is a weak acid, okay? That has to be your starting point. You need to look strong or weak to start. Once you've established that this thing is weak, now you can create the ionization equation. HOCl, aqueous, react it with water. The hydrogen proton is going to transfer. This is a weak acid, so equilibrium arrows. We're going to be left with the OCl negative aqueous plus hydronium, H3O plus aqueous. Totally the same question as what we did before, guys, right? The previous example. We start by saying, what are the concentrations initially? How do they change? And what will they be at equilibrium? Initially, we're told it has a concentration of 0.36 moles per liter. So a similar type question to the one that we were just doing before, right? Similar idea. We're going to end up with a different answer though. It is going to go down by X. So technically, this is 0.36 minus X. But because it is a weak acid, we take that to simply be 0.36. We don't worry about the minus X. Leave out water. Both of these will initially start at 0 because it hasn't ionized initially. Then as it ionizes, they will go up by one amount of x and x. 0 plus x is x. 0 plus x is x. How do we then figure out what x is? We need to have an algebraic expression where x is the only thing we don't know. What is that algebraic expression? It is the equilibrium law. Ka is equal to the concentration of the anion, OCl negative, times the concentration of hydronium, H3O plus, divided by the concentration of HOCl aqueous. Equilibrium laws exist at equilibrium. So we are focused at the equilibrium values, not the initial, not the changing. Plug in what you know. Ka was right from the data booklet, that page 8 and 9. It's 4.0 times 10 to the negative 8 equals. These are both x. How do I know? Because it's at equilibrium. X, x, this. Okay? So x times x, x squared goes on top. Vice versa, the concentration of the HOCl is going to go on the bottom at equilibrium. So I have that value divided by 0.36. Next thing we're going to do is take this thing and rearrange it. So x by itself is going to be equal to the square root of 0.36 times 4.0 times 10 to the negative 8, that Ka value. Take the square root of it. X ends up being equal to the wonderful value of 1.2 times 10 to the negative 4 moles per liter. In other words, guys, X is hydronium, so let's get that part done. H3O plus, 2 sig digs, 1.2 times 10 to the negative 4 moles per liter. So really, an identical process to what we did on the previous question, right? Same. Last step, if you have hydronium, you can get pH, which is part of the purpose of this question. pH equals negative log of the hydronium concentration. Plug in what you know. Negative log of 1.2 times 10 to the negative 4 moles per liter. Show your work, please. 3.92 is our wonderful pH. 2 sig dig, guys. Don't forget that only the 9 and the 2 are significant. 3 is just place value. Wow, there we go. We are done. Strong and weak acids. Strong and weak bases, I think I'm going to split into 2 podcasts. One of them based upon just the initial idea of talking about some simple questions and then introducing a relationship between KB and Ka. So here we go. A few questions I want you to attempt here, please. You should do number 5, 6, and 7 from your assignment before you listen to the 3rd podcast and relate a similar concept to strong and weak bases. Talk to you soon.